So I'd like to welcome everyone and thank you for attending our monthly College of Natural Sciences webinar. My name is Allison Sherwood. I'm the Interim Associate Dean for the college. Through our Pilina webinar series, we're aiming to reach the broader community and share the world-class research that happens both in the College of Natural Sciences, but also across the Manoa campus. Today's presentation features Dr. Doug Simons, who is the newly appointed Director for the Institute for Astronomy at the University of Hawaii at Manoa. Doug Simons received his Bachelor of Science degree in astronomy at the California Institute of Technology in 1985 and his PhD in astronomy at the University of Hawaii Institute for Astronomy in 1990 before working as a staff astronomer at the Canada-France-Hawaii Telescope, or the CFHT, for 4 years. Doug joined the Gemini 8-meter telescope project in 1994 as systems scientist, and as the Associate Director for Development, managed Gemini's instrumentation program for many years before becoming Gemini Observatories Director from 2006 to 2011. Doug returned to CFHT in 2012, where he served as Executive Director for nearly 10 years. In 2021, he returned to his alma mater, where he now serves as Director for the UH Institute for Astronomy. Doug has served on numerous community boards. Currently, he's on the board of the Kona Kahala Chamber of Commerce, and he's president-elect of the Hawaii Island Chamber of Commerce. He's an avid supporter of education as well as community outreach, and he's helped to develop a number of programs, including Envision Maunakea, Maunakea Fund, Maunakea Scholars, and the Ahua He Inoa. And so now I'd like to turn over our time to Doug for his presentation entitled Astronomy Futurecast.
Okay. Mahalo, Allison, and mahalo everybody for joining me this afternoon for a little presentation. I just had my afternoon cup of coffee, so I'm refueled officially. Should have enough to get us through. Let me do a screen share real quick and get started. And let's see, I'll shrink that. I'm going to go to full screen. Okay, so welcome to this presentation that I've given a number of times. Give you a little disclaimer. It's actually first shown all the way back in 2018 at Emilo Astronomy Center. And I've updated it a bit since then. I should probably go through and overhaul it at this point. I think at some point I got kind of tired of reporting past discoveries and was crazy enough to start to predict future discoveries. And that was the motivation for this. It's actually annual Maunakea Skies presentation that I provided for Emilo a few years ago. So with that, I'll do something a little unusual. I'll give you a musical trailer to start out with to give you an idea of the material I'm going to cover. Bear in mind, this was designed for a full projection system within Emilo, so I've sort of collapsed it to 2D, but I think it came out pretty well in any case. So I will rejoin you in just a few minutes after this trailer that shows where we're going to go with this presentation. And with that teaser, fasten your seatbelts. We'll head on into the presentation from here as I push PowerPoint pretty hard in this set of slides. This is actually a montage of pictures. The lower part is a picture I took in Alaska like 10 or 20 years or so ago of a mountain range there. And I like to use this as sort of a backdrop for the trail that I feel we're on sometimes, hiking along this plateau in front of us and ultimately into the mountain range there where things get really tight or difficult, with signposts along the way ranging from black holes to potentially life out there, detecting the first stars. And then you get onto the sort of the holy grails, if you like, understanding what dark energy is. Do we live in a multiverse or not? And the thing that I really get excited about is the possibility of new physics that you hear about from time to time. So what I'm going to try and do in this presentation is do my best to predict over the next decade or so the discoveries that are possibly out there in astronomy and astrophysics, given a variety of assumptions. But I so far, if you notice, there's a black hole image prediction in the previous slide set. I got that bit right at least. We'll see what other parts I get right over time. So first of all, let me remind everybody that astronomy is a highly technology-driven field. There are many in the audience who would recognize that fact. And to emphasize that, on the left-hand side, this is a really nice color rendering of the Mount Wilson 100-inch telescope that I remember seeing as a kid. I was born in the LA area. I think I was 6 years old. My dad brought me up to see this giant machine that I didn't understand at all. It was used, of course, for some groundbreaking research. Perhaps the most important thing that came out of Hubble was the discovery that the universe is in fact expanding, with the technology at the time being photographic plates. And over another 100 years or so, the technology has just radically advanced exponentially since then. And a good example of that would be, for example, the Gemini telescopes in Chile and Hawaii and the laser adaptive optics systems that they have employed over the years. And you see spectacular images like that in the lower right panel, which are really quite commonplace with the telescopes on Mauna Kea and around the world these days. So the idea behind all this to predict discoveries is to kind of mash up technology trends, which are fairly obvious now over the next decade or so, and research trends, and make a guesstimate as to what might be coming down the pipe in terms of discoveries over the course of this decade or so. So first thing on the list or the menu is research into black holes. And this is a graphic from, I think, the movie Interstellar, which was pretty good, I thought, up until the very end, where they kind of went off the rails, if you remember the movie. First of all, that's the pronunciation. The definition is a region of space having a gravitational field so intense that no matter or radiation can't escape. And as a father of three with kids in college, it also means a place where people or things, especially money, disappear without a trace. And I have one more year of one kid to get through college, and that black hole will finally evaporate. Black holes come in, broadly speaking, two very large, differently scaled masses. On the low end, you have black holes that are a few solar masses, a few times the mass of our sun. This is SS433, which is a symbiotic black hole. You see it nestled closely to a red giant star in this little animation, pulling material off of the outer atmosphere of the star, and it spirals in to relativistic speeds. That material forms a jet and does some really interesting physics as it oscillates around that star. On the other end of the spectrum, we have black holes that are billions of times the mass of our sun. So these would be in the cores of things we called quasars, which were discovered over 50 years or so ago at my other school, Caltech, at Palomar Observatory, I believe, is where they first discovered. So they share a lot of physics between them, but the scales are radically different between the two. Kind of like this chart because it shows in one swoop, if you will, the life history for stars. And the most important parameter in determining the future or the fate of a star is by far its mass. And on the left-hand side, you see a giant molecular cloud of which stars will collapse over time. And on the top branch, you see so-called small stars, so that would include our sun, that go through an evolutionary phase, become a red giant planetary nebula, in which they blow off the outer atmosphere and leave behind what's called a white dwarf, basically the nuclear core of the star at the end of their life cycle. And that can go on for roughly 10 billion years or so for a star like our sun. And on the bottom branch, you see a so-called large star, so that's at least a few times the mass of our sun. And those are unstable. They burn their fuel much, much faster, so to speak, than stars like our sun. Go through what's called a red supergiant phase, and eventually explode, forming supernova. And again, depending on the mass of the initial star, that defines, for the most part, whether or not it becomes a neutron star or a black hole. So the three types of outcomes, this is some of the beauty and the simplicity of stellar evolution, is that these are the outcomes you can have in essence. The vast majority of the time, a star will wind up at its end state is in what's called a white dwarf. That's about 97% of all the stars in the universe will become white dwarfs. Density is really high, 1 million grams per cc. Recall water is 1 gram per cc. Diameter is about 10,000 kilometers or so. The maximum mass is 1.4 times the mass of our sun. And it's held up by what we call electrostatic pressure of the electrons that are moving very high speeds within the white dwarf structure. If you get higher mass than that, up to say 3 or so, you form a neutron star. Those have ridiculously high densities, upwards of 10 to the 15th grams per cubic centimeter. For scale, I like to point out the neutron star is about the size of Maunakea. So you basically have been able to collapse an entire star into a volume that tiny. And they are held up, prevented from collapsing in any further by the mutual repulsion pressure of the neutrons. Essentially, protons and electrons are forced together to form neutrons, or something called neutronium in these stars. And then if you have higher masses than that, you form a black hole. Mathematically, you can argue that they have an infinite density. I'm of the camp that quantum effects probably take over and prevent the so-called singularity from forming, but that's speculation at this point. The outer diameter is characterized by something called the Schwarzschild radius. It's about 5 kilometers for a 1 solar mass black hole. So that's basically the radius within which not even light can escape from that object. The maximum mass is unlimited. You could, in principle, make an entire universe into a black hole, and we suspect that that's a real possibility depending on the mechanism to generate a universe. And as I said before, they collapse the space-time continuum into a singularity. So in principle, you could compress anything to a black hole if you were able to generate enough force. For example, if you wanted to be a black hole, you'd actually have to be less than the so-called classical diameter of a proton to squeeze the Earth into a black hole. It would be about the size of a marble, about 10 millimeters or so. And yes, you can have microscopic black holes. These have been searched for in particle accelerators. To my knowledge, they've never been demonstrated. If they are formed, they have extremely short lifetimes through something called Hawking radiation. So matter, time, and space is part of the story behind black holes. And this little graphic on the left, you may have seen in some form or another. That's intended to show the sun and the Earth. And the green mesh below is the space-time continuum in which they exist. And everything that has mass is manifest in the space-time continuum by warping it in some way, shape, or form. So you might think that light travels in straight lines. In fact, it travels along the lines of the local space-time continuum. So if you have light going near the limb of the sun or the edge of the sun, what in fact happens is it curves around the sun, and that was part of a really famous experiment a little after 1900 that Einstein predicted that would happen as a result of relativity. And time slows down relative to when you're in that sort of low gravity field, and you don't necessarily sense that yourself when you're in that warp space, but the relative time between in and out of that warp space is what changes. So black holes are a different animal altogether. In principle, once light falls in, it cannot escape because the escape velocity for that object is higher than the speed of light. And in principle, time itself stops in the interior of a black hole. Again, that's if you were able to survive that drop into a black hole, which is a process that's not likely, you wouldn't necessarily notice that the time was changing with respect to what you're used to. But from the outside perspective, it would absolutely slow down. So some of the state-of-the-art research that's ongoing here in Hawaii, and it's mostly been focused on the black hole in the center of our Milky Way galaxy. That's an animation that shows the orbits of stars around an object that was detected decades ago as actually a radio object called Sagittarius star. And the group at UCLA, using Keck Observatory over the years, have mapped out these orbits of stars. You see the years ticking along in the upper right-hand box there. And there's an invisible object that is responsible for those stars moving around that point in space. And when they actually get very close to it, they're actually whipping around at a significant fraction of the speed of light. On the right-hand side, you see flaring that was recorded actually more like 20 years ago, 10 or 20 years ago for the first time, in which material is being gobbled up into the event horizon, spiraling and superheating and being absorbed into the black hole itself. That's the only sort of infrared radiation signature that we've seen so far from these objects. So what's next in black hole research? Well, this is where I give you the first update. Many of you remember just a couple of years ago, a trio that won the Nobel Prize in Physics, including Roger Penrose, Reinhard Genzel, and Andrea Ghez, the latter doing her work for over 20 years or so at Keck Observatories. She's based at UCLA. And this is a real success story for Maunakea astronomy. Andrea is a great person, and she, you know, the epitome of a scientist who stuck it out, used the most advanced technology available to map out the positions of these stars as they circle around this invisible object, and produce some of the most compelling evidence early on that black holes do exist, and we have a very large one, about 4 million solar mass one in the center of our galaxy. Going beyond that, and also quite recently, is the Event Horizon Telescope, and that is a consortium of radio telescopes that you see pictured there on the picture of the surface of the Earth there, and the lines represent what are called baselines between those various radio telescopes across the entire Earth. In Hawaii, there are a couple of them. There's Smithsonian Millimeter Array and JCMT, otherwise known as East Asian Observatory, provided absolutely essential Western points in that entire array of telescopes for some really incredible observations that were made. So when you're able to assemble the data from an array that's roughly the diameter of the Earth, the resolution or the clarity of the picture that you record scales linearly with the size of the array, or the diameter or dimension, longest dimension of the array. And for this particular system, to scale it to, say, the size of a golf ball in LA, and when viewed from New York, you could actually resolve the dimples on the golf ball 5,000 miles or so away. To do this, and one of the real key technology advances was portable atomic clocks. These are now commercially available, and that's essential to essentially timestamp the data as it's recorded simultaneously from each radio telescope as they're all observing the object in conjunction with each other. And that way you can reconstruct an image with very powerful computers. This was first done in a really spectacular way with M87 and a supermassive black hole there that I'll show you a picture of, which you probably recognized. The next image, actually, I think it'll actually be a movie, will be of that 4 million solar mass black hole in the center of our galaxy. I haven't seen it myself yet. I'm in touch with the EHT group, and I believe we'll see the first suite of publications within a couple of months, I think. And there'll be quite the splash like there was before with what we dubbed here locally Povegi, which is the name provided by the Larry by Ohio program, and Larry Kimura, who's kind of the heart and soul of that whole program, provided the name Povegi, composed of Po, which is in the Kumulipo, the profound dark source of unending creation that is in that remarkable creation chant, and Vehi, which is the embellishment with beautiful light of the Po. So here's a nice little video produced by of that black hole, how it was recorded here in Hawaii, and the name.
It's enormous, and its size is larger than our entire solar system. And that's what we're imaging, is that gas that's flying around at that close to the speed of light, and then it's the light produced by it bent by the strong gravity of the black hole.
It immediately, of course, takes me to this major documentation, the source of darkness, Kumulipo. Povegi. Po is this fathomless powerful, ceaseless creation, darkness. Povegi is an adorning embellishment.
Povegi, as a name, is so perfect because it provides real truths about the image of the black hole that we see.
We look at it through the Hawaiian lens as genes, our genealogy. There is this connection between astronomy and this whole question about where we come from.
To be able to deliver the first image to the public of a black hole is really, really special.
So that was one of the most intense chicken skin moments I've had as an astronomer. I had the pleasure 2 weeks before it was released. That was a highly embargoed picture to see it myself when I was working with Larry and the team to develop the Hawaiian name for that object. And I confess, I actually had a hard time sleeping that night after I saw the first image of a black hole, because I never thought I'd live to see that. And that's such an incredibly bizarre region of space that it really just kind of shook me as a scientist that we actually pulled this off and were able to directly image the so-called shadow of a black hole. So black hole research on steroids is where we're headed now, with even more sophisticated equipment than what I just showed you with DHT, and that would be in the form of LIGO, which I'll show you in just a second. This is an animation of two coalescing black holes that in practice are actually going about 100 times faster than what you see in this animation. It's much slowed down. You see the sort of flow of space-time warping the image behind it as these two objects circle around each other and eventually coalesce into a single black hole. So there's some really interesting physics that occurs there at various levels. And one of the simplest ones, but also the most amazing ones, is captured in these diagrams, which you see two sort of medium-sized black holes merging or coalescing into one of them. So if you look at that first one, for example, that LIGO detected, the mass of the first black hole was analyzed to be 36 times the mass of our sun, and the second black hole was 29. So that adds up to 65, but it's possible to derive from the observation the measured mass of the resulting coalesced black hole, and that was 62, which begs the question, where'd three solar masses go to in just a fraction of a second, which is this spectacular amount of energy. And what happened, it was turned into a gravitational wave that propagated across the space-time continuum. Einstein predicted this a long time ago. And this incredible machine is able to detect that wave passing through Earth. I've had the pleasure of visiting this facility in LIGO. It's in Louisiana, and you're looking at the two arms, which I believe are 4 kilometers apiece, for a pair of lasers that are propagated from the central building there you see in that image. And the idea is it's basically a very sophisticated so-called Michelson interferometer, where there's a very powerful laser that's split by a highly precise beam splitter. Goes off of these reflectors, which by themselves are incredibly sophisticated pieces of engineering. And the beams are recombined where they are detected by an extremely sensitive optical detector. And the idea is that as the gravitational wave goes through this structure, the two arms of the interferometer stretch and compress by different amounts. That shifts the two beams in terms of a phase shift a little bit, and that creates what we call constructive or destructive interference and changes the brightness of the spot. And from that, we infer a gravitational wave. I would argue that LIGO currently is even more important than the telescope Galileo used roughly 500 years or so to detect the phases of Venus and rings of Saturn, because at that time, there are a lot of telescopes. He was famous for looking at the sky and actually recording it and importantly, publishing his results. I've always wondered if there were other Galileos before him that looked at these objects and simply didn't publish to advertise, if you will, what he discovered. LIGO is unique still. There's a lower sensitivity facility, it's called Virgo in Europe, that's used in conjunction with LIGO, and it is being pushed to its so-called quantum limit through a succession of upgrades. And if you can imagine, when you have a machine like that, there's a lot of tension between taking it offline to upgrade it further, because if you double the sensitivity of LIGO, the way the the math works out, so to speak. You increase the volume of space by about a factor of 8 in terms of sensitivity to gravitational waves. So the future cast for black hole research, there's a lot going on. Look for these new gravity wave facilities being built in India. Japan is building one right now. Europe has an extremely large one, at least on the whiteboard at this point. Look for cryogenic systems to be built into them. Space-based gravitational waves platforms, one called LISA that NASA's been developing, and even more sensitive receivers in the future. Also watch for possibilities for movies, like I mentioned before. I haven't seen it yet, but I have a hunch that the EHT group will actually not just release a picture, but a movie of the black hole in the center of our galaxy. We'll also be able to take sensitive black holes and do all kinds of really fascinating research, including trying to answer the question, are black holes in fact the source of dark matter in the universe? So next topic, first stars that I showed you in the trailer earlier, that was the same video. And the question here is exactly when and how did the first stars form after the Big Bang? And it's been a subject of intense research, as you can imagine, particularly by the larger telescopes that have the farthest reach, if you will, across the universe. And when the universe was young, after the Big Bang, for the first few hundred thousand years or so, there's essentially nothing but hydrogen and helium. This is the periodic table of the elements that you may recognize, and I was forced to memorize in chemistry class in high school. I don't know if the kids do that anymore these days, but I had it memorized at some point, long since forgotten. Back a long, long time ago in the history of the universe, the periodic table was much simpler, though, as I said, with essentially only hydrogen and helium, before there were stars to start to process all of that material into more complicated nuclei. And that processing occurred over time with the formation of galaxies. And these are two very sophisticated so-called hydrodynamic codes that show you it's actually the same region of space, a galaxy coalescing. Z is a time metric, and as it goes lower and lower, Z equals 0 is now. So you'll see that sort of stepping down, and that means it's going from a long time ago to the current time. On the left-hand side, that's visible light. On the right-hand side, the gray represents dark matter and the pink represents gaseous material. And you see these just incredible explosions that are occurring on the scale of this forming galaxy. Those are supernovae that are blowing up and basically showering material all around the galaxy. Some fraction of it comes raining down, in essence, back into the galaxy, having been enriched and fortified through that recurring processing over time. Back on the left, you see around at 0.6 something interesting happens, and the universe has expanded enough, and there's been enough so-called galactic cannibalism that's occurred that you now have these sort of isolated pinwheels that are spinning in space and have the sort of long-term stability to host stars, to host planetary systems, and to allow all of that chemistry, which is now possible with all the processing I mentioned before, to start to establish and evolve life. So sophisticated models, as I said, have been used to try and predict what these first stars look like, behave like, et cetera. We believe that they were much, much higher mass than stars today, somewhere around 100 to maybe upwards of 1,000 times the mass of our sun. They would have very, very short lifetimes, and of order, a few million years at the most, as opposed to say 10 billion years for our sun. So this first suite of stars, or a cohort of stars after the Big Bang, they didn't last very long at all, and they immediately filled a much smaller, more compact universe at that time with a lot of so-called processed material. Finding those first stars is a real challenge, and we have some astronomers in the audience today who appreciate that challenge. You need a very sophisticated equipment, although this particular experiment caught my attention when I saw it a couple of years ago for the first time, and decided to include it in this presentation. The audacity of the experiment, when you factor in its cost, is really impressive. So deep in the Australian desert, this little machine was set up and made a remarkable discovery that I haven't heard if it's been reproduced yet or not. But in essence, it was designed to look for the spectrum, or the fingerprint, if you will, of the first stars after the Big Bang, but in a very clever way. In the lower left little graphic there, you see the so-called cosmic dark ages. That's when there were no stars, and the conditions were just getting to the point where the universe was cooling off to where you could coalesce material into stars. And then we get into the so-called period of the cosmic dawn when stars first formed. And it was right in there that there was a prediction made that the stars in that very early period in the universe, just a few hundred thousand years, after the Big Bang, you would have been able to not necessarily see the light of those stars, but see the light being absorbed by material just in between those stars and our Earth today. It would form a dip in the spectrum, like you see there on the right. There's a nice little video that I recorded from Nature magazine that explains what that is. So I'll flip that on now.
Scientists think they've made the first measurements from the cosmic dawn, the period in the universe's history when the first stars began to shine. But how can scientists study something that happened more than 13.5 billion years ago? Well, to understand that, you need to start with hydrogen. Hydrogen is a cosmologist's best friend. They use it to study everything. You see, a quirk of hydrogen is that it can emit photons as it switches between states, specifically photons with a wavelength of around 21 centimetres. When astronomers point radio telescopes at the sky, they see a mess of different radio waves, but nestled in there is always that 21 centimetre line. These emissions from hydrogen have helped scientists to map the universe. It's how they discovered that we're sitting in a huge spiral-shaped galaxy, the Milky Way. But hydrogen isn't just useful for studying the universe today. Right after the Big Bang, the universe was a dark soup of electrons and protons. The particles soon clumped together as hydrogen, and after hundreds of millions of years, hydrogen collected into stars, generating light. Cosmologists call this the cosmic dawn. That primordial light is hard to see with a telescope because the tiny amounts of light made by the first stars would be extremely faint. So scientists have taken a slightly different tack. You see, when that light was first created, it changed everything, including the hydrogen itself, crucially making it able to absorb radiation at its favourite 21 centimetre line. With this in mind, rather than look for emission from hydrogen, cosmologists have looked instead for its absorption. They turn to the cosmic microwave background, the mess of radiation left over from the Big Bang. In theory, the moment light hit that early hydrogen, it would have started absorbing this radiation, and that should have left a blip in the CMB. And that, after decades of scouring for evidence from this time and 2 years of verification, is what cosmologists have found. But here's where it gets interesting. The signal they found is not at 21 centimetres anymore, because space itself is expanding. That line has stretched over time, which is handy for us because the amount of stretching, the wavelength the light is at now, tells us how long the light has travelled, and so when those stars formed. Finally, this allows scientists to put some dates to the beginning of the cosmic dawn. But that isn't all. While the time the first stars formed seems about right, the signal is way bigger than cosmologists predicted. A lot more radiation was absorbed from this cosmic microwave background than makes sense given what we know so far about the early universe. Something doesn't add up. And one tantalising possibility is that we may be seeing the influence of dark matter. Now, this is far from confirmed, but if true, it would give us a wealth of information about dark matter's properties and where to look for it. So this little blip could not only give us a snapshot of the first stars, but it could be the key to unlocking one of the biggest mysteries in physics.
So that experiment out in the outback, I guess, in Australia, cost about $5 million. National Science Foundation sponsored it. A lot of bang for the buck for that bit of taxpayer money, in my opinion. There's another experiment that was recently launched that you also likely heard about. That's a different scale of price, about $10 billion. That is going to revolutionize, I suspect, various aspects of 21st century astronomy. And that, of course, is the James Webb Space Telescope, which is a good segue into the next field of future casting I'll cover. So this is an incredible leap in technology. It's an infrared optimized telescope, about 6-meter aperture. You no doubt have seen pictures on the news about it. Due to the exquisite precision of its orbital insertion, I guess you call it, out at L2, They didn't have to use as much fuel, which means I think it's upwards of at least a 10-year lifetime now. Was originally projected about 5 years. You cannot service this unlike Hubble Space Telescope. So it's an extremely precious resource that will become operational, I suspect, in just a few months in terms of early science results. So I mentioned that there's a little scale model of JWST just to show you how big this thing is and the engineering marvel that it represents to be able to pack all that up into an Ariane 5 rocket and essentially self-assemble in space through several hundred individual steps, in which, of course, there's nobody out there with a wrench to fix it if you run into a problem. So this was an incredible engineering feat to pull this off. Some of the early science, as I said before, we anticipate will be not necessarily the first stars like I showed you in that other experiment, but certainly some of the very first embryonic galaxies made out of maybe the second generation stars that formed after the Big Bang itself. So future forecasts for those first stars, I certainly anticipate, if it's not already occurring already, verification of that radio signature of the first stars. That was a really clever experiment. And I wouldn't be necessarily surprised at all if they took it from a single point in the sky detection to potentially mapping out across the sky that signal to make a map of those first stars. The so-called extremely large telescopes will be used to look at these first protogalaxies along with JWST. The Webb will go deeper than big telescopes on the ground. And it will also be used for creating these exquisitely high resolution images of these protogalaxies. But Webb will be used for quite a bit more than that. And some of the most fascinating and exciting research, and I think near-term research, when they go live with JWST will be on exoplanets, which is the next topic in my future cast here. So this little set of images captures a tremendous amount of effort over the past several decades, arguably, but it's really coming to a crescendo now, in which you see TESS, which is the latest satellite that NASA has put in orbit several years ago that's mapping out nearby exoplanets, where nearby means out to about 100 parsecs, that's about 300 light years out from the Earth. And that is being used in conjunction with ground-based facilities. And not widely known, but we now have or very soon, we'll have 4 extremely high-performance instruments, Keck, Gemini, Subaru, and CFHT, designed to look at these objects, a lot of them initially detected by TESS, to characterize them in terms of mass. And in essence, this combination of TESS and ground-based facilities will find the needles in the haystack. And those needles are the exoplanets that are transiting nearby stars that JWST can be used to measure those transits and try and detect the composition of the atmospheres of those exoplanets as they pass in front of these nearby stars. It's an exquisitely complicated and sensitive measurement to try and measure the chemical composition of an exoplanet's atmosphere. And the model on the left shows you, for example, some of the stronger so-called biomarkers in Earth's atmosphere, oxygen being one of them. Ozone is another one, though you can generate those through somewhat exotic processes outside of life. But in any case, I think this is one of the most elegant and impressive range of capabilities in space and on the ground that maybe astronomy's ever assembled to attempt to accomplish this incredible feat, otherwise known as detecting life beyond Earth. And it's going to happen. I mean, Webb is out there. These measurements are going to be made. We've got equipment on the ground, and like I said, millions of dollars of new equipment on Mauna Kea. So this is a really exciting time for astronomy, I think. Just because I'm a former director of CFHT, I'll zoom in on that particular one of those 4 instruments, an instrument called Sphero. It's about a $15 million instrument. You see pictures there of the team in France while they were assembling this giant cryostat and infrared spectrograph. It's received 300 nights on CFHT. It will likely receive at least that again in what is certainly one of the largest exoplanet searches ever attempted from Mauna Kea. I like to point out it's the first instrument in the world to use the so-called H4RG, Hawaii, it's not Hawaii, it's just H4RG. It's a 4,000 by 4,000 pixel near-infrared sensor that was actually in large part developed in the building that I am right now at IFA Hilo by a wonderful guy called Don Hall, previous director of the Institute. And wish Don was around to see his baby being deployed in Webb, and these incredible instruments that are being used for exoplanet research right now. These are just little videos of the actual integration of this rather huge instrument at the third floor Coude room at CFHT. So future cast for exoplanets, well, there's an armada of space and ground-based equipment that I mentioned before. Not to mention all the robotic equipment that NASA has launched to the nearby planets. Mars, of course, is a focus of intense research. So it seems like every time we have a near pass, if you will, between Earth and Mars, there's another launch, not just from NASA, but from other countries to put orbiters or landers on Mars in search for life. As I said before, on Mauna Kea, we have 4 new instruments. They must total $50 million, I bet, easily, of investment to sort of lead the charge from the ground, in my mind, for exoplanet research. If TMT is built, and I'm pulling for it, obviously, it will be a quantum leap in all of these areas for exoplanet research, given the light gathering grasp of that beautiful telescope. And I'll stick my neck out a little bit, but I wouldn't be surprised if what I call exolife is detected within a few decades. And that's mostly a statement about the incredible array of research and instrumentation and technology development, all dedicated to searching for life. At some point, I will actually be more impressed that we haven't found life than we do find life with all the activity going on in that whole field of research right now. Which brings me back to sort of full circle back to Galileo and some of the early research he did to sort of frame and contextualize this search for life for you. He's a very famous individual, of course, and was revolutionary as a so-called dynamicist, in which he was able to use telescope technology at the time. And I've had an opportunity to look through a replica of Galileo's telescope. I was in the Galileo Museum in Florence, Italy, and I saw the original telescope that he used, and it's taken a beating over the years if you haven't seen it. But looking through the replica, it's like looking through a keyhole. It has almost no eye relief, and it's really impressive for me that he was able to do what he did. On the left-hand side, you see the first images, so to speak, of a solar system. Of course, that would be ours, and the crescent phase of Venus, which was very convincing evidence that we lived in a heliocentric solar system. And you saw the rings of Saturn there in the top right. And it took 400 years to go from that first image, albeit sketched on paper, to the second image of a planetary system, which I'm very proud to say is an image taken from Mauna Kea. Those 3 white dots are exoplanets, each about 10 times the mass of Jupiter, orbiting the star, which has been blotted out by that white dot. There's actually 4 planets that were detected with a little bit more observations from Mauna Kea. And I tend to liken all of this as sort of a 21st century version of the exploration by Polynesians and other great explorers in search of islands, if you will, where our islands are in the sky at this point. They're in the form of planets, as opposed to islands on the surface of the ocean. But this type of discovery has roots that go a long, long ways back with the technologies of the time. And we may have been searching for different islands. They are, in a sense, all looked at as sort of harbors for life and harbors for future. So at some point, I don't think I'll necessarily live to see it, but at some point, we will have technology, I'm convinced, to send robots, not necessarily people, but at least robots, to the nearest stars. NASA's got some really amazing propulsion technology development going on. And when I ask myself, what good does this research do, particularly the research now, in which it's really focused heavily on nearby terrestrial class exoplanets. These are the objects that, as we are discovering them, will be looked at in decades ahead as the first exoplanets to target these interstellar probes. They'll have to be smart, autonomous. They'll have to be able to go into a capture around these exoplanets and find their way back, obviously, to complete that mission. But for me, we're kind of the map makers at this early stage in this process, and future generations will use these maps to direct their advanced spacecraft in the future, like we're doing in interplanetary space, but we'll do at some point in interstellar space. So with that, I'll share with you one final video that for me brings back a lot of very good memories of a hero of mine. And I suspect a hero of yours as well when you hear the voice that's narrating this. This person, among other factors, got me involved in astronomy when I was just a kid. And I thought that this video beautifully captures that sense of discovery and exploration that I'm trying to convey through this wonderful search for exoplanets.
We were hunters and foragers. The frontier was everywhere. We were bounded only by the earth and the ocean and the sky. The open road still softly calls. Our little terraqueous globe is the madhouse of those 100,000 millions of worlds. We who cannot even put our own planetary home in order, riven with rivalries and hatreds, are we to venture out into space? By the time we're ready to settle even the nearest other planetary systems, we will have changed. The simple passage of so many generations will have changed us. Necessity will have changed us. We're an adaptable species. It will not be we who reach Alpha Centauri and the other nearby stars. It will be a species very like us, but with more of our strengths and fewer of our weaknesses. More confident, far-seeing, capable, and prudent. For all our failings, despite our limitations and fallibilities, we humans are capable of greatness. What new wonders, undreamt of in our time, will we have wrought in another generation and another? How far will our nomadic species have wandered by the end of the next century and the next millennium? Our remote descendants, safely arrayed on many worlds through the solar system and beyond, will be unified by their common heritage, by their regard for their home planet, and by the knowledge that whatever other life may be, the only humans in all the universe come from Earth. They will gaze up and strain to find the blue dot in their skies. They will marvel at how vulnerable the repository of all our potential once was, how perilous our infancy, how humble our beginnings, how many rivers we had to cross before we found our way.
So you'll no doubt recognize the voice of Carl Sagan. He was a revolutionary of his time and, like I said, inspired, I think, a generation to fall in love with the field of astronomy and astrophysics. I recall distinctly watching on PBS late nights, I think it was Saturday nights in the 90s when I was a kid, being just captivated by Carl's Cosmos series. And that really led to a whole array of science documentaries and things of that sort we just didn't have prior to Cosmos. So I like that video because it really does a nice job with the imagery to capture the humanity, the sense of discovery, and the frontier that we have covered over the history of our many generations, and the possibility for taking that human spirit and extending it well beyond where we are now in a field of science exploration and discovery that is simply unmatched in the history of our species. I feel very strongly that astronomy is the epitome of sciences that is all about exploration and discovery. You know, when we kind of slice through space with an array of radio telescopes and record an image of a black hole, that is just amazingly awe-inspiring to be able to marshal all the resources and put together all the bits and pieces of technology to make that possible, all the way to the James Webb Space Telescope and the incredible array of instrumentation that we have on Mauna Kea right now for doing groundbreaking research as well. So I'll close off with just a few final thoughts to share with you to try and button up the whole presentation for you. First of all, defying all odds. We likely exist in an infinitely large realm, making us infinitely small. And I have a whole presentation, maybe someday I can come back to share with you why I claim that. Through our determination and intellect, we're beginning to map our place in our vast home, helping satisfy our insatiable need for context and meaning. That's what I'm trying to do with the final slides here, to give you a sense of how big these discoveries are and the foundations that are being laid for future generations with that knowledge in place. We're on the cusp of learning if we as life forms are common or as rare as existence itself. And then finally, I like to remind people that we each ride a wave of life that crests in our time. And that wave we're riding now is like any our ancestors encountered. And my humble advice to everyone is simply enjoy the ride. So with that, mahalo for your time and patience with the presentation. I tried to bring it in for a safe 3-point landing at 3 o'clock. We're at about 2:58, so not bad. We arrived a couple minutes early. Remember that next time. So I played through the credits for the various videos and things that I stole from lots of sources around to assemble the material for this presentation. And someday, if you're in Hilo and we're back to doing the Mauna Kea Skies presentation at Imiloa, I look forward to doing these and other presentations and the full dome projection system there and having a lot of fun with them. So mahalo everybody, and I'll stop the screen share there.
Thank you so much, Doug. That was wonderfully inspirational. And certainly the context makes me feel very, very small right now, which is good. So at this point, we'd like to open it up for questions. If anybody in the audience would like to ask a question of Doug, feel free to just unmute your microphone, or you can put your question into the chat box.
Yeah, this is Danny Quintana. Can you hear me?
Yep, I hear you fine.
Yeah, I love the presentation. My second to last book is Copernicus Was Mistaken, Why the Earth is Still the Center of the Universe. And your presentation confirmed in my mind exactly what I was talking about in that book. This Earth is so precious because everything else is so far away that this is what is relevant. And
right.
I'm really impressed. And I think once we improve our propulsion systems, we'll be able to further explore the inner solar system, what we have. And I don't know if there is life on Europa under that ocean, but my guess is there probably is some type of microbial life. What is going on with our propulsion systems with NASA? Because we abandoned the NERVA program decades ago, which was really unfortunate. And do you see nuclear power as a viable source for propulsion?
Yeah, there are a variety of ion propulsion systems that are sort of in experimental phases. And you see them occasionally with small sats that they're using. The most exotic propulsion I've seen are the so-called Q thrusters or quantum thrusters. And there's been, his last name is White, I forget the first name, the guy who runs the Advanced Propulsion Unit at NASA. He's got some really interesting YouTube videos if you want to look him up. And the Q thruster technology, which is sufficiently outlandish that it's suspect in terms of its physics. But if he's on the right track, that's a really incredible technology that you could use by his estimates. Essentially a small nuclear reactor, where small is the kind of thing you'd find in a nuclear submarine, to be able to provide enough energy with the Q thruster for sort of a 50-year round trip to the nearest star. So that's the most extreme technology that I'm aware of NASA working on, and I'm by no means an expert. Good question, though.
Are there other questions for Doug?
They're all thinking about Carl Sagan now. I'm thinking about Carl. I wish I had a chance to meet him.
Well, I'll ask another question. What do you think the probability is that there is life, microbial life on Europa and on Venus?
I actually wouldn't be surprised, put it that way. I just find the probabilities of life being unique to Earth as so outlandish that, like I hinted, if we ever come to a conclusion that there is no life with a high degree of confidence beyond Earth, that to me is shocking, and there's something very deep going on with that conclusion. But I honestly wouldn't be that surprised. There's material being shared between the planets that's well documented. There are life forms that can exist within the extreme conditions of interplanetary, if not interstellar space. I've wondered if there, as many have, if there isn't this sort of background, if you will, of sort of prebiotic material that is populating the surfaces of planets and connecting everything together is sort of one stream of initial life forms. But first things first, we got to find it on somewhere other than Earth, see if it has similar DNA. I think that'd be one of the most interesting tests, and I'll go out from there. So I'm in that camp. I'm a pro-life exoplanet guy that I think in time we will find it one way or another.
Oh, I think that's right. With Drake's equation, it's probable that there is life out there, but that's what makes life here so unique. Our organization is working on public education on saving the wildlife in the oceans, and I really appreciate what the University of Hawaii is doing with us. So our website is savingoceans.org, and your presentation just inspires me to continue the work because it is precious. It is absolutely unique. I do get concerned that we're reaching out to other star systems because if they can get here, they can kill us.
Yeah, I don't think we're worth it. That's my theory. You put too high a value on us. Sam's iPad has a question.
Go ahead, Sam. You can unmute to ask your question.
Okay. I was a little surprised to hear you say that Galileo had seen the rings of Saturn, and you didn't mention that he saw the moons of Jupiter. I've always told my students that it was the other way around. So I'm just curious.
Yeah, that's just because that particular, I don't think it included the Galilean satellites. But you're absolutely right. He had I think it was over the course of just a couple of weeks in December in the 1500s, and I have in my mind the sketches that he made of the Galilean satellites as they orbited, and that too is convincing evidence of the sort of dynamic nature of the solar system. But he did detect the rings of Saturn. Wasn't able to see the Cassini division or anything like that, but was able to do so. And the fact that he observed the phases of Venus, though, which was just overwhelming evidence that we live in a heliocentric solar system, for which he, of course, paid the price. Jackie.
Aloha, Doug. So my question has to do with the skies. I just came back from New Mexico, and while I was there, I noticed a lot of reflection in the sky, and I'm noticing more here at home as we put up more satellites and so forth. And I'm wondering your thoughts on how that will impact the future of discovery and astronomy.
Yeah, good question, and not widely known. The so-called mega constellations that are being thrown into low Earth orbit are pretty disturbing. The first wave of that, I'm sure you've heard, is the SpaceX Starlink satellites that are designed basically to put a global internet in place. And while the ambition is altruistic in the sense of trying to get internet worldwide, there's a price to be paid when you do that. The worst case projections I've heard are basically 100,000 low Earth orbit satellites launched within the next 10 to 20 years. And that for me is going to fundamentally transform the appearance of the sky in ways that I absolutely do not like, either as a somebody who just likes to go out in the evening and look at the stars. I started as an amateur astronomer. For astronomy, this means that particularly in the evening and morning hours when you have the illumination of those satellites just right, there's going to be a lot of so-called streaks within images recorded by telescopes on the ground. This is a really big deal. It kind of snuck up on us, in my opinion, and astronomy is trying to catch up to this tsunami of stuff that's being put into low Earth orbit that is a confluence of a really odd set of circumstances. We have essentially a trillionaire in the form of Elon Musk, and we have a technology of low-cost launch capability that you're seeing in the form of SpaceX, and you're seeing essentially and completely unregulated field. The so-called Space Act back in the 60s did not contemplate a trillionaire being able to throw up 10,000 satellites, right? So it's the 21st century of the Wild Wild West, and getting our hands around that is going to be very hard. And it's not going to be that long. You're going to go outside and you're going to see 100 satellites moving, and it's going to be just for me heartbreaking. I want to see Orion. I don't want to see your damn satellites. so it's not widely known, and I is both an astronomer and someone who just likes to see the night sky. I have my worries about that. Thanks for reminding me.
No, thank you, Doug, because from an indigenous perspective, I'm finding that those of us who have traditional relationships with the skies are having to rethink and revisit our traditions and our values and so forth. So thank you very much.
Are there any final questions for Doug? Well, I think at this point we'll go ahead. I'd like to thank Doug again for his presentation. That was really fabulous. I really appreciate you coming to speak with us today. I'd also like to thank all of you for coming and attending our webinar series. And we look forward to seeing you hopefully at next month's presentation. So our next event is going to be held on Wednesday, May 18th at 2 p.m. HST. It's going to feature Dr. Megan Porter. She's a faculty member in the School of Life Sciences for the College of Natural Sciences. And she's going to be speaking about light, vision, and perception, how animals see the world. So watch your inboxes for your invitation to that event. Thank you again, Doug. Thank you all for attending today. And we hope you have a wonderful rest of your day or evening. Aloha.
Aloha, everybody.